This lecture will provide you information about traditional surveying techniques and some of the ways that they work. In this lecture, we'll cover some of the different types of surveying as well as the three traditional approaches that we'll be using in this class. So the tape and compass approach, the level and rod approach, and the total station approach. Each of these techniques can stand alone or can be used in conjunction with GNSS position information. Additionally, each of these techniques has its advantages and each has its disadvantages, and you should know and be able to describe what the advantage and disadvantage of each technique is. Surveying is the science and art, really, of determining what the relative positions of points above, on, or below the surface of the Earth are, and locating these points in the field. So here we see an example of a total station survey, for example, conducted along Pensacola Beach, Florida in November 2015. Here we're surveying the beach state, the beach slope as part of a research project. There are two broad categories of surveying. First of all, plane surveying is done with the reference base for fieldwork and computations assumed to be a flat horizontal surface. This approach is generally acceptable within and up to a 12-mile radius of any single point because the pull of gravity within that distance is nearly parallel at all points. So essentially the horizontal lines can be considered straight. Beyond that 12 miles, the curvature of the Earth begins to affect the line of sight within the survey and begins to affect the survey results. So the second type of surveying that we'll cover is geodetic surveying. Geodetic surveying is a technique to determine the relative positions of more widely spaced points, lengths, and directions. Now, this requires the consideration of the size and shape of the Earth, something that planar surveying does not. So in other words, geodetic surveying is an approach that's useful for all size areas, small or large, but is also capable of accounting for the abnormal size and irregularities in the size and curvature of the Earth's surface. So there are benchmarks spread across the entire United States which can help you tie your survey into geographic coordinates. So benchmarks such as the one pictured here can provide you with the exact location and or elevation at that location. The location coordinates given on these benchmarks are in reference to WGS 84, and the elevation provided is the orthometric height in reference to NAVD 88. So while many benchmarks will have both the location and elevation information, so the X, Y, and Z information, it's important to note that not all benchmarks have both pieces of information. You may have some which only have the vertical or only have the X and Y location information. So if you're conducting an elevation survey, only one benchmark is required. This means that the direction will be arbitrary. So given a single reference point, there's no way to determine, or define, I should say, the direction of the X or Y axes. So while this approach may be useful in some instances, it's more likely that you want your survey directions fixed in some meaningful way. If you have two benchmarks, then you can clearly define what the direction is for any surveyed point. In other words, the X and Y directions are referenced to some known coordinate system. So if your two benchmarks are managed by the U.S. National Geodetic Survey, such as the one pictured here, then your coordinates would be tied to that WGS 84 datum. The most primitive surveying technique is using a tape measure and compass, or tape and compass. Now, many states were initially surveyed and laid out using this approach. It relies on the technique of taping, which is applying a known length of a graduated tape directly to a line a number of times. When much of the U.S. was being surveyed, the conventional graduated tape was called a chain, and this corresponded to 66 feet long and was composed of 100 links. Today we may have field tapes large enough to cover from the origin to the point being surveyed and can measure that distance without having to tape that distance. Surveying an area using this approach can either be done using a radial approach or a radiation approach. And this is where you maintain a single origin or benchmark for the entire survey, and you simply rotate around that point to get the locations of all other surveyed points. Or the tape and compass approach can be done using a traverse approach. Now this is where you actually compute the location of one point, such as point A here, and then you move your survey origin to point A and you survey out point B. Now that survey off of point B is done off of point A. So you then proceed throughout the area of interest, making sure to tie everything back to your initial origin benchmark. When using the tape and compass approach, it's essential that you take detailed notes and sketch a clear field map of the survey, including measured angles and distances. Without this detailed sketch and information, it can actually be very difficult to understand what your numbers mean when you're looking back at the survey information and to reconstruct your survey or what you were surveying. The tape and compass example on the previous slide was done assuming that the area was flat horizontal surface. Now, tape and compass can also be done across an uneven surface. However, the computations become a little more complicated. So in this class, we won't be conducting a tape and compass survey across an uneven surface, but instead we'll make the assumption that the area is a relatively flat horizontal surface. So if you were, though, to survey an uneven surface using the tape and compass approach, you would need to keep detailed notes of the starting height and ending height of every survey line. Now this is used to reconstruct the elevation change from one point to the next when you're surveying. So while the tape and compass approach is an acceptable approach to surveying an area, it also has the greatest chance for user error. It can be extremely difficult to precisely measure the angle to any particular point, and even a measurement error of a few degrees can quickly add up to a large position error. This is especially important for points spaced far apart. Additionally, distance measurements are more likely to have error introduced by the user measuring the distance. The level and rod approach represents an improvement on the tape and compass approach. So the level and rod surveying technique uses a sighting level and marked rod to compute distance and direction. So the level picture here in the upper right has a dial at its base. Now this dial allows the user to more precisely measure the angle to a particular point that they're surveying. So the first step is to sight the level along some reference line. Now this reference line can be anything, but it's important to remember that this reference line will set the orientation of the X and Y axes for the entire survey. To get the angle to a surveyed point, simply rotate the sighting part of the level, or the top part of the level, until the crosshatches are lined up with the rod. Now, the rod should be located over top of the point you're surveying. It's essential to note that you do not rotate the dial at the bottom of the level when rotating the sighting part of the level. This will throw off your angle measurements and cause your angles to be much more complicated. But if you maintain the position of that dial at the bottom, that angle dial, you will be able to precisely measure the angle from your reference line to that survey point. Now, you want to measure and record the angle, the upper crosshatch, the middle crosshatch, and the lower crosshatch. So for this example, let's say that you measured an upper crosshatch as 1.205 meters. You measured the middle crosshatch as 1.155 meters, and you measured the lower crosshatch as 1.005 meters. To get the horizontal distance from the level to the rod, simply subtract the lower crosshatch from the upper crosshatch and multiply that value by 100. So in this case, subtracting 1.005 meters from 1.205 meters, you get 0.200 meters. Multiply this value by 100 and you get a horizontal distance of 20 meters. That 20 meters is the distance from the level to the rod. Now to get the elevation difference between the level site and the point being surveyed, simply subtract the middle crosshatch measurement from the instrument height, or the height from the ground to the line on the sighting level. It has a line located on the actual level. In this case, so we assume that the sighting level is located approximately 1 meter off the ground. So if we subtract that middle crosshatch measurement of 1.155 meters from the instrument height of 1 meter, we get an elevation for the surveyed point of negative 0.155 meters. Now, this indicates that the surveyed point is actually 0.155 meters below the location that the sighting level is located at. So you continue this approach in either a radial or traverse approach. However, using a radial approach minimizes the amount of work that you have to do to complete the survey. So instead of having to move the level and tripod multiple times and re-level it and reset your reference point, you only need to set it up once if you go with a radial approach, which for this class we will be using the radial survey design. The third and most accurate surveying technique that we'll cover in this class is using a total station. Now, this approach is used actually extensively to survey utilities such as water, electric, sewer lines, and to lay out and survey construction projects and footings, and even to survey beaches and other natural environments, as I showed earlier. So for a total station survey, you need the total station unit itself, which is pictured on the upper right here, and one or more prisms. And the prisms are actually attached to a rod, so they're elevated off the surface. So the total station integrates an electronic transit and an electronic distance meter to read the slope distance from the instrument to the point represented by the prism. So you move the prism out to a particular point you're interested in surveying, you run this, it calculates the slope and the distance, and calculates the x, y, and z. So the unit's capable of many other complex functions, such as shooting around corners. You can also georeference points ahead of time. However, in this class, we'll only be using it in open environments, essentially to measure straight line distance. So the hypotenuse of a straight line distance from the total station to the prism is based upon the time it takes for the laser to reach the prism and to return to the total station. Now, the elevation is computed by subtracting d from the prism height and subtracting this value by the instrument height. So both of these calculations are done internally by the unit, though. You don't need to be concerned with them. Just understand how the system works, how it calculates the position. When using a total station alone without any external reference points or benchmarks, the direction and orientation of the x and y axes are arbitrary. The x and y axes are set by the unit internally, and it's not in any particular direction. It's not necessarily x or y is aligned north or south or east or west. It's also important to note that this is only the case for simpler total station units. Some newer units actually have integrated compasses and or GPS receivers. Now, if it has a GPS receiver and or compass, that can enable the unit or the total station to actually orient its axes to the north, south, or some other predefined direction. All positions throughout the total station survey are with respect to the location of the total station and the arbitrary axis, at least as we will deal with in this course. So, in order to reference the survey to a known coordinate system, you need to include two known benchmarks. Now, including these benchmarks will enable you to either set the coordinate system internally within the unit, or as we'll do in this class, to transform the surveyed points into a known coordinate system after the fact. This transformation can be done many different ways. However, in this class, we'll use a simple Excel spreadsheet to compute the transform coordinates, and you'll do this for the different approaches. So you'll transform the coordinates from the tape and compass, from the level and rod, and from the total station all into geographic coordinates, so they'll have meaningful geographic locations. The actual coordinate transformation process itself is actually a matrix algebra problem, with non-aligned isometric rectilinear coordinate system. Don't worry, we won't have to worry about that. We won't be dealing with that. It's already set up in an Excel spreadsheet. So the total station surveys are typically done in a radial approach because you don't have to spend a lot of time breaking down equipment, moving equipment, and then resetting it up, recalibrating it, remeasuring the height, and inputting that information. So this concludes the traditional surveying lecture. You need to know a couple things. First of all, what are the three traditional surveying approaches? And second, how do they work? Third, what are the advantages and disadvantages of each? So we went over the tape and compass, the level and rod, and the total station approach. What are the advantages, disadvantages of each, and how does that relate to how each technique works? Also, you should know that which technique is most accurate and which is least accurate, and why. Now, this was suggested throughout the lecture based on the progression of surveying techniques from tape and compass through to level and rod through to total station.